You are sitting somewhere familiar, a room you have occupied before. Your body feels continuous, intact, predictable. The floor beneath you appears solid. Time seems to be moving forward in the usual way. Cause precedes effect. Objects exist where you expect them to be. Nothing feels strange. You trust this feeling without thinking about it. You trust that the world around you persists when you are not paying attention. You trust that space is there, that time flows, that events happen in a definite order, that you are a single observer moving through a stable reality. Science helped build that trust. You were taught that the universe is governed by laws, that those laws are precise, consistent, and objective, that while reality may be complex, it is ultimately coherent, that paradoxes are signs of misunderstanding, not features of the world itself, but that confidence is fragile. Because beneath the surface of modern physics and mathematics, contradictions do not disappear. They accumulate. They persist. They survive every attempt to remove them, and some of them are not philosophical curiosities. They are embedded directly into the equations that describe how reality works. In these paradoxes, objects exist in multiple states. Events occur without a clear cause. Information refuses to be destroyed. Time stops behaving like a sequence. Observation alters outcomes retroactively, and systems that should be impossible appear to be mathematically unavoidable. None of this comes from speculation or imagination. These problems emerge from real experiments, real measurements, and real theoretical frameworks that successfully predict the world you live in. The question is not whether these paradoxes exist. The question is what it means that reality continues to function with them unresolved. What follows is a descent through 9 of the most unsettling paradoxes known to science, not because they are mysterious, but because they are precise. Not because they are unsolved, but because solving them may require abandoning assumptions you rely on to feel that the world makes sense at all. 1. The paradox of observation. You assume that reality exists independently of you, that objects have properties whether or not you are looking. That measurement simply reveals what was already there. This assumption feels unavoidable, but at the smallest measurable scales, it fails. Physical systems do not behave as though they carry definite attributes waiting to be uncovered. Instead, outcomes appear to depend on whether observation occurs at all, and how it occurs. The act of measurement does not merely record reality, it participates in its formation. This is not a philosophical position. It is a consequence of experiments that have been repeated for decades with increasing precision. When you isolate a particle and remove all attempts to observe it, its behavior cannot be described as having a single, definite state. It exists instead as a spread of possibilities. Not uncertainty in your knowledge, but uncertainty in the system itself. The equations do not say the particle has a hidden value you have failed to detect. They say no value exists yet. This distinction matters. In everyday life, ignorance can be corrected. If you do not know the position of an object, you can look again. The object was always there, waiting to be found. At quantum scales, this logic collapses. Before measurement, the system does not contain a fact to be revealed. It contains a range of potential outcomes, none of which are privileged until interaction occurs. When you perform a measurement, the system responds by producing a definite result. But the theory does not describe this as uncovering a pre-existing reality. It describes it as a transition. Something discontinuous happens. A cloud of possibilities resolves into a single outcome. And crucially, the theory offers no internal explanation for why this happens at the moment of observation, rather than earlier. You might expect observation to be an active process, a disturbance, a physical interaction that changes the system. But this explanation fails in carefully designed experiments where disturbance is minimized or eliminated. Even when no energy is transferred in a way that could classically alter the system, the mere availability of information changes the result. What matters is not force, but knowledge. This leads to an uncomfortable implication. If outcomes depend on observation, then reality is not fully defined until it is observed. The world does not consist solely of objects evolving in time. It also includes conditions under which those objects become definite. Observation is not outside the system. It is woven into its structure. You might try to locate the boundary, to say that microscopic systems behave this way, but macroscopic ones do not. But experiments steadily erode this distinction. Larger and more complex systems exhibit the same dependence on measurement. The only reason you do not notice this behavior in everyday objects is that they are constantly interacting with their environment. They are being observed, in a sense, all the time. This does not restore comfort. It removes isolation. It suggests that definiteness itself is a relational property. Things are not simply what they are. They become what they are through interaction. At this point, you may ask who or what qualifies as an observer: a human consciousness, a measuring device, the environment. The theory does not answer. It uses the concept of observation without defining it physically. This is not an oversight. It is a structural gap. The equations require an observer, but they do not contain one. The paradox is not that observation changes reality. The paradox is that reality appears incomplete without it. The laws that predict outcomes with extraordinary accuracy rely on a process they cannot describe from within. They work only by assuming a transition they cannot model. This forces a quiet reversal of perspective. You are not simply a spectator watching a finished world unfold. You are part of the mechanism by which the world acquires definite features. Not because you are special, but because observation itself is fundamental. And once this is accepted, a deeper question emerges. If reality depends on observation, then what existed before observers arose? If the universe evolved long before any measuring entities appeared, in what sense was it definite? And if definiteness requires observation, then the universe may not have been fully real in the way you intuitively imagine. The paradox of observation does not suggest that reality is imaginary. It suggests something more precise and more unsettling. That existence may be conditional, that facts are not merely discovered. They are brought into being by the very act of asking what is there. 2. The measurement problem. You expect physical processes to evolve smoothly according to fixed laws. Yet quantum theory introduces a rupture. Between measurements, systems follow one set of rules. At measurement, they abruptly follow another. There is no clear boundary between these regimes, no physical definition of what qualifies as an observer. The theory works, but only by relying on a transition it cannot internally explain. Reality appears to require a moment where its own rules suspend themselves. This rupture is not subtle. It sits at the center of the most successful predictive framework ever constructed. When a system is not being measured, its evolution is continuous, deterministic, and precisely governed by mathematical equations. Possibilities spread and interfere. Causes lead to effects in a smooth, unbroken way. Nothing jumps, nothing selects, everything evolves. Then measurement happens. At that moment, the description changes completely. The system no longer evolves, it resolves. One outcome appears, all others vanish. The transition is instantaneous, discontinuous, and not described by the same laws that governed the system moments earlier. The theory simply instructs you to switch rules. You are not told when this switch occurs. You are not told what physical condition triggers it. You are only told that it must happen because experiments demand it. This is the measurement problem. You might assume that measurement is just another physical interaction, that when a particle hits a detector, ordinary dynamics apply. But this explanation fails under scrutiny. If measurement were only interaction, then the same smooth equations should apply throughout. There would be no need for a second rule, no collapse, no rupture. Yet the mathematics insists otherwise. The problem is not that quantum theory lacks precision. It is that it is too precise to hide this inconsistency. The theory predicts probabilities with extraordinary accuracy, but it cannot explain how probability becomes fact. It describes potential outcomes, not actual ones. The moment when one outcome becomes real is inserted by hand. You might try to define measurement pragmatically. A measurement occurs when information is recorded, or when a system becomes irreversible, or when a macroscopic apparatus is involved. But none of these criteria are fundamental. They are descriptions from within the world, not principles built into the theory. The equations do not recognize macroscopic scales. They do not privilege complexity. They do not contain a variable labeled observer. This creates an unsettling picture. Reality appears to require an undefined event in order to function. A moment when possibility becomes actuality without a physical mechanism to justify the transition. The universe evolves according to strict rules, until suddenly it does not. Some interpretations attempt to remove the rupture by denying collapse altogether. Others attempt to explain collapse as an emergent process. None of these resolutions are experimentally distinguished. All reproduce the same predictions. The measurement problem persists not because it is poorly understood, but because every solution changes something fundamental about what reality is. If collapse is real, then the laws of physics are incomplete. They describe evolution but not realization. If collapse is not real, then outcomes never become singular, and the definiteness you experience must be explained another way. Either way, something you take for granted becomes questionable. Consider what this means for objectivity. You assume that events happen independently of how they are observed. But if measurement plays a constitutive role, then facts are not simply out there waiting. They arise through interaction with systems capable of registering them. Objectivity becomes conditional, not absolute. You might feel tempted to push this problem aside. After all, the theory works. Technology based on it functions flawlessly. But that success sharpens the paradox. The measurement problem is not a failure of prediction. It is a failure of explanation. The world behaves as though two incompatible descriptions are both required. This forces a reconsideration of what physical law is. You expect laws to apply universally, without exception. The measurement problem suggests that at least one law is conditional on context, that the universe needs a place where its own description ends and something else begins. And once you accept that, a deeper unease follows. If the transition from possibility to fact is not governed by physical law, then it may not be governed by anything within physics at all. The moment when reality becomes definite may lie outside the framework designed to describe it. The measurement problem does not claim that reality is incoherent. It claims something quieter and more disturbing. that coherence may require an unresolved gap, that the universe works not despite this rupture, but with it embedded at its core. 3. Schrödinger's cat was never a thought experiment. You are told the cat is a metaphor, a way to illustrate uncertainty, but the mathematics behind it does not remain safely abstract. The same logic governs real particles, real detectors, and real experiments performed daily. According to the equations, superpositions do not collapse automatically. Without an observer, they persist. This implies that unresolved outcomes are not hypothetical. They are physically allowed. The discomfort comes not from imagination, but from taking the theory seriously. The story is often softened for convenience. A cat in a box sounds absurd, so you are encouraged to treat it as a teaching device, something exaggerated to make a point. But the equations that lead to this scenario make no distinction between cats and electrons. They scale without apology. What applies to the smallest components of matter applies, in principle, to any system not perfectly isolated from quantum rules. You assume that somewhere along the chain from particle to apparatus to animal, definiteness must emerge naturally. That reality surely resolves itself before reaching macroscopic objects. But the theory does not provide such a boundary. It does not say when superposition becomes impossible. It does not say that size, mass, or complexity forces a collapse. Left to itself, the mathematics allows the ambiguity to persist indefinitely. This is not because physicists failed to notice the problem. It is because the problem refuses to disappear. In the formal description, the radioactive atom, the detector, the poison mechanism, and the cat become entangled. Not metaphorically, but mathematically. Their states are linked into a single combined system. If the atom is undecayed, the cat is alive. If the atom decays, the cat is dead. Before observation, neither outcome is selected. The system exists in a superposition of both possibilities at once. You may want to say that the cat must feel one outcome, that consciousness resolves the ambiguity. But this simply relocates the problem. If the cat is conscious enough to collapse the state, then consciousness has physical power. If it is not, then the ambiguity remains until an external observer intervenes. The theory does not specify which is correct. What makes this unsettling is not the imagery. It is the implication that nothing in the formalism prevents unresolved outcomes from extending upward indefinitely. The world you experience as definite may be the result of constant observation, not inherent stability. Modern experiments confirm this logic in increasingly complex systems. Superpositions have been demonstrated in large molecules. Interference effects appear in systems far removed from isolated particles. Each result reinforces the same conclusion. The rules do not stop applying just because the system looks familiar. You might argue that environmental interactions solve the problem, that constant contact with surroundings forces systems into definite states. This process, known as decoherence, explains why superpositions become effectively unobservable. But decoherence does not produce outcomes. It suppresses interference. It explains why possibilities stop interacting, not why one becomes real. The cat problem remains untouched. Decoherence tells you why you never see alive and dead cats. It does not tell you why you see either alive or dead at all. This distinction is easy to overlook, but it is central. Suppressing ambiguity is not the same as resolving it. The equations still describe a superposition. The definiteness you experience is not derived, it is assumed. At this point, the discomfort deepens. If superpositions persist without observation, then reality itself may remain indeterminate until measured. The world does not continuously collapse into facts on its own. It waits. This forces you to reconsider what you mean by existence. You tend to think of objects as having properties regardless of whether anyone is paying attention. Schrödinger's cat suggests that this assumption is not guaranteed by the laws of physics. Definiteness may not be automatic. It may be conditional. The paradox is not that a cat could be alive and dead. The paradox is that the theory describing reality permits unresolved states, and yet your experience never includes them. Somewhere between the equations and perception, something happens that the theory does not explain. Schrödinger's cat was never meant to be taken lightly. It was designed to expose a fracture, a place where formal success conceals conceptual failure. The longer the theory survives experimental scrutiny, the harder it becomes to dismiss the implication. The problem is not imagining an impossible cat. The problem is realizing that the mathematics describing the real world does not forbid it. 4. The delayed choice paradox. You believe the past is fixed, that once an event has occurred, no future decision can alter it. But experiments suggest otherwise. Choices made in the present can determine whether a particle behaved like a wave or a particle in the past, not metaphorically, operationally. The system's history appears incomplete until measured. Cause and effect lose their familiar direction, and time stops behaving like a clean sequence of events. Your intuition about time is built on order. First, something happens, then it leaves a trace. Later events can react to it, but they cannot reach backward and change what already took place. This assumption feels so basic that questioning it seems meaningless. Yet, in carefully designed quantum experiments, this order becomes ambiguous. The delayed choice paradox arises from situations where a particle's behavior depends on how it is measured, even when that measurement choice is made after the particle has already entered or even exited the experimental apparatus. You would expect the particle to have already committed to a particular behavior. Either it traveled as a localized object or it spread out like a wave. But the experimental outcomes suggest that this distinction is not settled until the final measurement occurs. In these setups, particles are sent through arrangements where they could exhibit wave-like interference or particle-like paths. The key detail is that the experimenter delays the decision of how to measure the particle until after the particle should have already decided how to behave. According to classical reasoning, the particle's past behavior should be independent of a future choice. According to the data, it is not. What is disturbing is not that the measurement affects the result. That is already familiar. What is disturbing is that the measurement appears to define the particle's prior state. The system does not behave as though it carried a definite history all along. Instead, its history seems conditional, shaped retroactively by how it is ultimately observed. You might try to say that the particle was always both a wave and a particle, and that measurement simply reveals one aspect. But this explanation quietly reintroduces the assumption the experiment undermines. It assumes a hidden, well-defined past. The formal description does not support this. The theory does not assign a single, observer-independent history to the system. From the mathematical perspective, the particle's evolution is described as a superposition of possibilities. These possibilities extend forward in time without committing to a specific narrative. Only at measurement does the system resolve into a concrete outcome. Until then, asking what really happened is not a well-posed question. This reframes the role of time. You are used to thinking of the past as complete and the future as open. The delayed choice paradox suggests that, at least at fundamental levels, both may be incomplete. The past is not a finished record waiting to be uncovered. It is a structure that only becomes definite when constraints are applied in the present. Importantly, this does not mean that signals travel backward in time or that causality is overtly violated. No usable information is sent to the past. The paradox is subtler. It is about explanation, not communication. The causal story you tell about the system depends on choices made later, even though no physical influence propagates backward. This undermines the idea that events have intrinsic narratives. You are accustomed to believing that every event carries a history independent of how it is later examined. The delayed choice experiment suggests that this belief may be an artifact of macroscopic experience, not a feature of reality itself. As experimental variations become more refined, the paradox grows harder to dismiss. Versions of delayed choice experiments have been implemented with increasing separation in time and space. The pattern persists. The description of what happened refuses to detach itself from how it is finally measured. This forces an uncomfortable conclusion. Reality may not be constructed as a sequence of settled facts extending backward from the present. Instead, it may resemble a web of potential, histories that only crystallize when observation imposes a framework. Time, in this view, is not a container in which events sit. It is a parameter within a process that does not fully resolve itself until interaction occurs. You live as though the past is immutable. The delayed choice paradox suggests that this confidence may be misplaced, not because the past changes, but because it may never have been as fixed as you assume. 5. Entanglement and the death of local reality. You assume distant objects are separate. That influence requires proximity, that nothing happening here can instantly affect something far away. Entanglement violates this intuition. Measurements performed on one particle immediately constrain the outcomes of another, regardless of distance. No signal travels between them. Nothing moves. Yet the correlation is exact. Either reality is non-local, or properties do not exist until measured. Both options contradict how you think the world should work. Your understanding of space depends on separation. If two objects are far apart, you expect them to behave independently unless something connects them. Forces weaken with distance. Signals take time. Cause spreads outward. This logic is not philosophical. It is built into everyday survival and into classical physics itself. Entanglement breaks this logic cleanly and repeatedly. When two particles become entangled, their properties are no longer independent. They must be described as a single system, even when separated by vast distances. You can send one particle across the room, across the planet, or across space itself. The description does not change. The system remains unified. When you measure one particle, the outcome you obtain immediately restricts the possible outcome of the other. This happens instantaneously, regardless of how far apart they are. There is no delay, no gradual influence, no detectable transmission. You might suspect hidden communication. Some signal traveling faster than light. But decades of experiments rule this out. The correlations appear without any exchange of information that could be exploited or intercepted. Nothing observable travels between the particles at the moment of measurement. What changes is not the distant particle itself, but the structure of what can be known about it. The moment you measure one side, the other side's outcome becomes constrained in a way that cannot be explained by shared history alone. This creates a dilemma with no comfortable resolution. One option is to accept non-locality, to admit that reality allows connections that do not respect spatial separation. That distance is not a fundamental barrier, that the universe, at a deep level, is not assembled from independent parts arranged in space, but from relationships that ignore it. The other option is to deny that properties exist prior to measurement. In this view, neither particle carries a definite state on its own. The correlations are not revealing hidden attributes. They are generating outcomes in tandem. Measurement does not uncover reality, it completes it. Both options dismantle something you rely on. If reality is non-local, then space is not the organizing principle you assume. If properties do not exist until measured, then objects are not the self-contained entities you imagine them to be. Either way, separateness becomes an approximation, not a fact. You might try to preserve locality by introducing hidden variables, unseen parameters that determine outcomes in advance. But careful tests rule out this possibility under reasonable assumptions. The correlations observed are too strong. Any hidden variable explanation must abandon either locality or realism. You cannot keep both. This is not a fringe conclusion. It is built into the structure of the experiments themselves. The predictions of quantum theory are not merely strange. They are incompatible with the idea that distant objects carry independent, pre-existing properties. The unsettling part is not speed. No usable information travels faster than light. Causality, in a practical sense, remains intact. What collapses is the picture of the world as a collection of separate things interacting locally. Entanglement suggests that separateness is emergent, not fundamental. You experience yourself as localized. Your body occupies one place. Your thoughts occur here, not elsewhere. Entanglement hints that this sense of localization may be superficial. At a deeper level, the universe may not decompose cleanly into independent pieces at all. Instead, it may consist of a single, interconnected structure that only appears divided when interactions suppress correlations. What you call an object may simply be a region where entanglement has been diluted enough to mimic independence. This reframes what distance means. Space no longer guarantees separation. It becomes a bookkeeping device for interactions, not a fundamental divider of reality. 2 points can be far apart in space and still belong to the same indivisible system. Entanglement does not tell you which interpretation is correct. It tells you that at least one of your core assumptions must be wrong. Either the world is non-local, or it is not fully real until measured. The death of local reality is not dramatic. It is quiet, it is mathematical, and it is supported every time the experiment is run. 6. The many worlds escape that solves nothing. You might try to restore order by multiplying realities. If all outcomes occur, then no collapse is needed. But this solution comes at a cost. Every quantum event branches the universe. Identity fractures. Probability loses its meaning. And you are forced to accept that countless versions of you continuously diverge without interaction or confirmation. The paradox is not eliminated. It is distributed across an unobservable infinity. The appeal is immediate. If the equations never collapse a system into a single outcome, then perhaps they never should. Perhaps the smooth, deterministic evolution of quantum states is all that ever happens. Measurement does not select a result. It reveals which branch you now occupy. Nothing mysterious occurs. No rules are suspended. The rupture disappears. At first, this seems like clarity. In this picture, the universe does not resolve uncertainty. It expands to accommodate it. When a quantum event has multiple possible outcomes, reality splits. Each outcome occurs, but in a different branch. From the inside, you experience only one. From the outside, all persist. The equations become simpler. The cost is conceptual. Every interaction, no matter how small, produces divergence. Not just dramatic experiments, but ordinary events. A photon reflects or does not. A molecule vibrates this way or that. The branching is constant, relentless, and unimaginably vast. Reality becomes a structure with no single history, only a continuously fracturing tree of alternatives. You do not notice this because you are confined to one branch, but this confinement raises a problem. If all outcomes occur, what does probability mean? In a single outcome universe, probability reflects uncertainty about what will happen. In a many outcome universe, everything happens. There is no uncertainty in the global description. Probability must then be reinterpreted as a measure of how often versions of you observe certain outcomes across branches. But this move is not automatic. It requires assumptions about how to count branches, how to weight them, and why you should expect to find yourself in one rather than another. The theory does not supply these answers. It replaces one gap with several. Then there is identity. You experience yourself as continuous, one person making choices over time. In a branching universe, this continuity fractures at every quantum event. There is no single future you. There are countless successors, each experiencing themselves as the continuation of the present moment. Which one is you? You might say all of them. But this stretches the concept of identity until it loses coherence. If every possible outcome is experienced by some version of you, then personal survival becomes ambiguous. So does responsibility. So does meaning. You cannot interact with these other versions. You cannot confirm their existence. You cannot distinguish this framework experimentally from interpretations that deny branching altogether. The multiplication of realities occurs entirely beyond observation. This raises a quiet but serious concern. The many worlds interpretation removes collapse by asserting an unobservable infinity. It restores mathematical elegance by abandoning empirical economy. Nothing in your experience forces you to accept the existence of these parallel branches. They are introduced to preserve the form of the equations, not to explain new data. And even within this framework, the original unease remains. You still observe definite outcomes. You still experience a single world. You still must explain why experience tracks one branch rather than another. The theory explains why outcomes exist. It does not explain why you observe this one. In attempting to remove the observer from the center of quantum theory, many worlds makes the observer unavoidable. Your perspective becomes the only thing that selects a narrative. Reality contains everything. Experience selects almost nothing. The paradox has not been resolved. It has been relocated. Instead of asking how possibilities collapse into facts, you now ask why facts feel exclusive in a universe where nothing ever resolves. Instead of explaining definiteness, you explain its absence everywhere except where you are. The many worlds escape offers consistency at the cost of intuition, testability, and parsimony. It trades one mystery for an infinite hierarchy of unseen realities. Whether this is a solution or a surrender depends on what you are willing to give up. What remains is the same discomfort. The world you experience is sharply defined. The theory that describes it is not. And multiplying realities does not explain why your experience insists on being singular. 7. The problem of time in fundamental physics. You experience time as constant motion, a steady progression from past to future. Physics does not. At the deepest level, time may not exist as a variable at all. The equations describing the universe remain unchanged, whether time flows or not. Change becomes an emergent illusion. If time is not fundamental, then neither is causality. Events do not happen. They simply are. Your intuition about reality is organized around sequence. One moment replaces another. Causes precede effects. You remember what has happened and anticipate what has not. This structure feels inseparable from existence itself. Without time, nothing could occur, nothing could change, nothing could matter. Yet when you examine the equations used to describe the universe at its most fundamental level, this structure quietly dissolves. In several foundational formulations of physics, time does not appear as a driving parameter. The equations describe relationships between states, not evolution through moments. They do not require a universal clock. They do not privilege a direction. From the perspective of these equations, the universe does not unfold. It is complete. This is not a poetic claim. It is a mathematical one. When physicists attempt to combine quantum theory with gravity, time begins to vanish from the formalism. The variables that describe geometry and matter remain, but time drops out. The resulting descriptions are static. They encode correlations, not motion. There is no built-in distinction between before and after. This creates a profound tension with experience. You feel time passing. You measure it. You build technologies that depend on it. But the deeper the theory goes, the less it resembles a process unfolding in time. One response is to treat time as emergent. In this view, time is not fundamental, but arises from more basic relations. Change is not built into reality. It appears when systems are described relative to one another. One configuration is compared to another, and the comparison is interpreted as temporal flow. This is not entirely unfamiliar. You do not observe time directly. You infer it from change. Clocks do not measure time itself. They measure motion, decay, oscillation. Time is the pattern you impose on these processes. But if time is emergent, then causality becomes fragile. Cause and effect rely on temporal order. If time is not fundamental, then neither is the idea that one event produces another. Instead, the universe becomes a network of correlations that you interpret as causes only because of how you are embedded within it. This reframes what an event is. You think of events as things that happen, points in time where the world changes. In a timeless framework, there are no events. There are only states, complete configurations of reality that coexist within a larger structure. You are not moving through these states. You are part of them. The sense of flow arises because your conscious experience is asymmetric. You retain records of some correlations and not others. Memory points in one direction, anticipation points in another. This creates the impression of passage, even if the underlying structure is static. What you call the present becomes a perspective, not a location. There is no objective now slicing the universe into past and future. Different observers, moving differently, already experience different divisions. A timeless description takes this further. It denies that there is a universal division at all. This raises an unsettling question. If the universe does not evolve, what does it mean to explain anything? Explanation usually traces a chain through time. One thing leads to another. If time is not fundamental, then explanation becomes relational rather than historical. You do not ask how something came to be. You ask how it fits. The problem of time does not deny your experience. It challenges its status. It suggests that what feels most immediate and undeniable may not be a feature of reality itself, but of how reality appears from within a particular configuration. You live as though time carries you forward. Fundamental physics offers a colder picture, one where the universe does not move, does not progress, and does not change. One where the flow you feel is something you generate, not something the universe provides. If this is correct, then the deepest paradox is not that time behaves strangely. It is that you experience it at all. 8. The block universe and the illusion of now. You believe the present is special, that it moves, that it separates what has happened from what has not. Relativity rejects this distinction. All moments coexist within a single structure. Past, present, and future are equally real. The sensation of flow exists only within conscious experience. From the outside, nothing moves. You are not traveling through time. You are embedded within it. Your sense of now feels undeniable. There is this moment, and then it passes. Another replaces it. The world seems to update itself continuously, frame by frame. You feel located at the leading edge of reality, with the past fixed behind you and the future open ahead. This feeling is so persistent that it feels like a property of the universe itself. Relativity quietly dismantles it. In the relativistic description of space-time, there is no universal present, no global slice that everyone agrees is happening now. Observers moving differently disagree about which events are simultaneous. What is present for one observer can be past or future for another. This is not a limitation of perception. It is a consequence of how space-time is structured. If there is no single present that all observers share, then the idea of a moving now loses its physical meaning. There is no objective boundary sweeping forward through the universe, converting future into past. Instead, all events exist within a four-dimensional structure. Space-time is not something that evolves. It is something that is. This is the block universe. In this view, every moment you remember and every moment you anticipate is equally real. Your birth, your future decisions, distant stars exploding long after you are gone, all occupy their own locations in space-time. Nothing comes into existence or fades away. The entire history of the universe is laid out as a static whole. What you experience as flow is not the universe changing. It is your perspective moving within the block. Or more precisely, it is a sequence of experiences embedded within different regions of the block, each containing records of other regions. You do not observe time itself. You observe correlations. You carry memories that point toward certain regions of space-time and expectations that point toward others. This asymmetry creates the impression of motion, but nothing in the underlying structure requires it. From the outside, nothing is happening. This reframes what change means. You think of change as something unfolding. In the block universe, change is replaced by difference. One region of space-time differs from another. The universe does not change over time. It contains change as part of its structure. You may find this unsettling because it threatens freedom. If the future already exists, how can your choices matter? But this objection misunderstands the picture. Your choices are part of the block. They are not overridden. They are included. The fact that a decision exists in space-time does not make it any less your decision. What disappears is the idea that the future is open in an absolute sense. Openness becomes perspectival. From within the block, you do not know which future region you will experience next. From outside, all regions are already there. This creates a strange duality. From your perspective, the future feels uncertain. From the structure of reality, it is fixed. Both descriptions are correct, but they apply at different levels. The illusion of now arises because your conscious experience is localized. You do not experience the entire block at once. You experience one slice, one configuration, one set of correlations. Each such experience contains records of others, creating a directional narrative. The block universe does not deny experience, it reclassifies it. The flow you feel is not a fundamental feature of reality. It is a feature of how certain structures within reality represent other structures. This removes a familiar comfort. The idea that the present is special gives you a sense of immediacy and control. If all moments are equally real, then the present loses its privileged status. It becomes just one location among many. You are not standing at the center of time as it unfolds. You are located within a fixed space-time structure, experiencing one region at a time. The universe is not keeping pace with you. It is already complete. The illusion of now is not a mistake. It is a consequence of being a system that can only access itself locally. But once you see through it, the world becomes quieter, heavier, and far less dynamic than it appears. 9. The grandfather paradox was never the real problem. Time travel paradoxes seem absurd, but modern physics allows closed time-like curves under certain conditions. The deeper issue is not killing your grandfather. It is whether consistency can be enforced at all. Some solutions suggest that paradoxical actions simply cannot occur. Others imply self-consistent loops where cause and effect collapse into the same event. Free choice becomes constrained by logical necessity. You are taught to treat time travel paradoxes as jokes, clever puzzles with obvious contradictions. If you go back and prevent your own existence, something must break. The conclusion feels reassuring. Reality, you assume, would never allow such a situation to arise. Physics is less confident. Within certain solutions to the equations of general relativity, space-time can curve in on itself. Paths through space-time can loop back to their own past. These closed, time-like curves do not require fantasy devices or narrative tricks. They emerge naturally from the mathematics under extreme conditions. Whether such conditions exist in nature is uncertain. That they are permitted by the theory is not. Once closed, time-like curves are allowed, the question shifts. It is no longer about dramatic acts of interference. It is about logical consistency. If an event lies on a loop, it must be compatible with itself. Every cause must already include its effect. Every effect must already be its cause. This creates a world where contradictions are not resolved by branching or erasure, but by exclusion. Certain actions simply never occur. Not because they are prevented by force, but because they would produce inconsistency. The universe enforces coherence by making some choices impossible. This is the self-consistency principle. In such a framework, you may feel free to choose, you may deliberate, you may act, but the set of actions available to you is silently restricted. You cannot make a choice that would disrupt the consistency of the loop. If you attempt to, circumstances will conspire to prevent it. Not dramatically, quietly. Something slips, a tool breaks, a decision changes. The paradox dissolves without announcement. What is unsettling is that nothing in this picture requires intention or enforcement. No guardian of causality intervenes. The structure of space-time itself filters outcomes. Only self-consistent histories are realized. You might try to preserve freedom by imagining branching timelines, but this returns you to the same problem encountered before. Branching explains contradiction by multiplication, not by resolution. It avoids inconsistency by placing it elsewhere. The self-consistency approach does something colder. It forbids inconsistency outright. This reframes what choice means. You tend to think of choice as the ability to select among all logically possible actions. In a self-consistent universe, logical possibility is constrained by global structure. You may feel free locally, but globally, the outcome is fixed. This does not mean your decisions are irrelevant. They still occur. They still matter. But they occur within a framework that already includes them. The loop is not imposed after the fact. It is the fact. Cause and effect lose their hierarchy. There is no first event in a closed loop, no origin point where explanation begins. Events explain each other circularly. This is not a failure of logic. It is a different kind of logic, one where linear ordering is replaced by mutual consistency. The discomfort comes from recognizing how easily this structure generalizes. You do not need literal time travel to encounter it. Any system where global constraints override local freedom exhibits the same tension. The universe may not need loops in time to enforce consistency. It may already do so through laws you interpret as necessity. The grandfather paradox distracts because it is personal and vivid. It invites you to imagine dramatic interference. The real problem is quieter. It is the possibility that the universe does not allow contradictions by permitting alternatives, but by denying them in advance. If this is true, then free will is not the power to do otherwise in an absolute sense. It is the experience of choosing among options that are already consistent with the total structure of reality. You choose, but you could not have chosen differently without breaking the world. The paradox is not that time travel creates contradictions. The paradox is that a universe capable of preventing them may already limit choice more tightly than you are comfortable admitting. 10. Information cannot be destroyed. You expect destruction to be final, burning, erasing, annihilating. Physics disagrees. Information appears to be conserved at all costs. Even black holes, once thought to erase everything, seem required to preserve information somehow. This creates contradictions between quantum mechanics and gravity that remain unresolved. Reality refuses to forget. Your everyday experience tells you that loss is permanent. Paper burns, files are deleted, bodies decay. Once something is destroyed, whatever pattern it once held seems gone forever. This intuition feels fundamental. Without irreversible loss, nothing would ever truly end. Physics quietly contradicts this assumption. At the most fundamental level, the laws governing particles and fields preserve information. The precise state of a system at one moment uniquely determines its state at all other moments. Even when matter changes form, scatters, or thermalizes, the underlying information is not erased. It is redistributed, scrambled, and hidden, but not destroyed. This is not a philosophical preference. It is a mathematical requirement of quantum theory. If information were truly lost, the equations would break. Predictions would become inconsistent. Probabilities would stop adding up correctly. The theory demands that information survives every process, no matter how violent. For a long time, black holes appeared to be the exception. Black holes seem to offer a clean endpoint. Matter falls in. Radiation leaks out. The internal structure disappears beyond an event horizon. Whatever information described the original system appeared irretrievably lost. This was not merely an inconvenience. It was a direct contradiction between quantum mechanics and general relativity. General relativity describes black holes as regions from which nothing escapes. Quantum theory insists that information must escape somehow. Both theories are extraordinarily successful in their domains. Both cannot be fully correct in this situation. This is the black hole information problem, but its implications extend far beyond astrophysics. If black holes destroy information, then quantum theory is incomplete. If black holes preserve information, then space-time behaves in ways that defy classical intuition. Either outcome forces a revision of something fundamental. Decades of theoretical work increasingly favor information preservation. Subtle correlations in radiation, holographic descriptions of space-time, and deep connections between geometry and entropy all suggest that information is not lost, even in the most extreme conditions. It is encoded in ways that are effectively impossible to reconstruct, but not fundamentally erased. This distinction matters. Loss that cannot be reversed in practice is not the same as loss in principle. Reality seems to allow only the former. No matter how chaotic a process appears, the underlying information remains. This creates an unsettling picture of the universe. Nothing ever truly disappears. Every interaction leaves a trace. Every configuration is embedded somewhere in the total structure of reality. Forgetting is a feature of limited observers, not of the universe itself. You experience memory as fragile. Your past fades. Records decay. But physics suggests that the universe remembers everything, even when no one can retrieve the record. The arrow of time you experience as decay and loss may not reflect a fundamental erasure, but a one-way dispersal of information into forms you cannot access. This reframes destruction as transformation without deletion. At the deepest level, reality behaves like a ledger that never resets. You can rearrange the entries, scramble them beyond recognition, bury them under layers of complexity, but you cannot remove them. The tension becomes sharper when you consider gravity. Space-time curvature seems to permit regions that permanently hide information. Quantum theory refuses to allow this. Reconciling the two requires rethinking what space, time, and locality mean. In many modern approaches, space-time itself emerges from patterns of information. Geometry becomes secondary. What you think of as space is a way information is organized. In this view, losing information would be equivalent to tearing holes in reality itself. The fact that the universe appears to prevent this at all costs suggests that information is not just something reality contains. It may be what reality is made of. You live as though the past can be erased. Physics suggests otherwise. Every moment you pass through leaves an imprint that never fully vanishes. The universe does not offer true destruction, only concealment. Reality refuses to forget, even when you do. 11. The black hole information paradox. You imagine black holes as endpoints, regions where physics breaks down. But when information enters a black hole, quantum theory insists it must remain recoverable. General relativity insists it cannot escape. Both theories work independently. Together, they conflict. Resolving this paradox may require abandoning space-time as fundamental or redefining what information even means. Your intuition tells you that black holes are places where things end. Matter crosses a boundary and vanishes. Causes terminate. Explanations stop. This picture feels natural because black holes seem designed to erase. They hide their interiors behind an event horizon and allow nothing to return. General relativity supports this intuition. According to its equations, once something crosses the event horizon, it is permanently cut off from the rest of the universe. No signal, no particle, no influence can escape. From the outside, whatever fell in might as well no longer exist. Quantum theory refuses this conclusion. Quantum mechanics demands that information is preserved, not in a practical sense, but in principle. The exact configuration of a system at one time must be encoded in its configuration at any other time. If information disappears completely, the theory loses coherence. Predictions become impossible to define consistently. When these two frameworks meet at a black hole, the contradiction becomes unavoidable. According to quantum theory, black holes are not perfectly black. They emit radiation. Over extremely long timescales, they evaporate. As they do, they lose mass and eventually disappear entirely. If this radiation is purely thermal, as early calculations suggested, it carries no information about what fell in. The black hole forms, evaporates, and leaves behind a universe missing pieces of its past. This outcome violates quantum mechanics. If the radiation somehow encodes the information, then the event horizon cannot be a one-way boundary in the way general relativity describes. Information must escape, not as matter or signals, but as subtle correlations spread across the radiation. Space-time behaves differently than expected. Neither option is comfortable. If information is lost, quantum theory is incomplete. If information escapes, space-time is not what general relativity says it is. The paradox does not arise from speculative physics. It arises from combining two theories that have both been tested with extraordinary success. Attempts to resolve the paradox have led to increasingly radical ideas. Some suggest that information is stored on the event horizon itself, smeared across its surface. Others propose that space-time inside the black hole is encoded elsewhere entirely, in ways that do not resemble ordinary geometry. In these approaches, what you think of as three-dimensional space emerges from deeper informational structures. This shifts the problem. Black holes stop being regions where information is destroyed and become regions where your intuitive picture of space fails. Another possibility is that space-time itself is not fundamental. It may be an effective description that breaks down under extreme conditions. Information remains primary. Geometry adapts to preserve it. What looks like an endpoint is instead a transformation into a different representation. This reframes what a black hole is. Not a hole in reality, but a reorganization of it. The unsettling part is that resolving the paradox seems to require abandoning at least one of the concepts you rely on to make sense of the world. Either locality, causality, or the independence of space-time must give way. There is no resolution that leaves everything intact. You may wonder why this matters beyond astrophysics. Black holes are distant, extreme, rare. But the paradox is not about location. It is about consistency. If physics cannot agree on what happens to information in one situation, then the foundations of explanation are unstable everywhere. The black hole information paradox exposes a fault line in your understanding of reality. It shows that the concepts of space, time, and information cannot all be fundamental in the way you assume. Something must be derivative. Something must give. You expect physics to describe what exists and how it changes. The paradox suggests that existence itself may depend on how information is encoded. Space may be a secondary effect. Time may be an ordering of records. Information may be the only thing that truly persists. Black holes do not destroy information. They destroy your assumptions about what reality is made of. 12. Reality as an error-correcting code. You think space is continuous, smooth, infinitely divisible, but emerging theories suggest space-time behaves like a discrete structure that actively protects information from corruption. The geometry of reality may be derived from quantum error correction. Space does not host physics. Physics generates space. What feels fundamental may be the byproduct of deeper constraints. Your intuition about space comes from touch and sight. Surfaces feel continuous. Distances seem infinitely refinable. You imagine that if you keep zooming in, space will always be there, filling the gaps. Classical physics reinforces this picture. Fields vary smoothly. Coordinates can be subdivided without limit. At the deepest levels explored by modern theory, this picture begins to fracture. Attempts to reconcile quantum mechanics with gravity increasingly suggest that space-time is not a primitive backdrop. It behaves more like a structure that emerges from underlying informational relationships. In some of the most developed frameworks, the geometry of space can be mathematically reconstructed from patterns of quantum entanglement and error correction. This is not an analogy. It is a precise correspondence. In quantum information theory, error-correcting codes protect information from noise by distributing it across many degrees of freedom. No single part contains the full message. Damage to a local region does not destroy the information. It can be recovered from the whole. This redundancy is not optional. It is required for stability. Remarkably, similar structures appear in theories of space-time. In these models, regions of space behave like encoded information. Local disturbances do not destroy the underlying data. Geometry remains stable because the information defining it is spread non-locally. What you perceive as a smooth spatial region is the visible surface of a deeper, fault-tolerant code. This changes the role of space completely. Space is no longer where physics happens. It is what physics produces when information is organized in specific ways. Geometry is not input. It is output. The unsettling implication is that space exists because information is protected. If space-time were continuous in the way you imagine, it would be fragile. Small disturbances could tear it apart. Singularities would destroy structure completely. But if space-time is an error-correcting system, then its resilience makes sense. It survives extreme conditions by design, not accident. This perspective reframes black holes, horizons, and even locality itself. Regions that appear isolated may still share information through non-local encoding. What looks like separation in space may be a convenient representation of a deeper unity. You tend to think of information as something stored in space, files on disks, patterns in matter. These theories invert that relationship. Space is the way information is stored. Location is a property of encoding, not of substance. This explains why information preservation appears so stubborn. If reality itself is structured to prevent informational loss, then conservation is not a law imposed on the universe. It is a consequence of how the universe is built. The geometry you move through every day may be a derived concept, like temperature or pressure, real, measurable, but not fundamental. Beneath it lies a layer of abstract relationships that do not resemble space at all. This also changes how you think about distance. In an error-correcting framework, 2 points can be far apart geometrically and still be closely linked informationally. Locality becomes approximate, useful, but not absolute. What you experience as smooth continuity may be the macroscopic effect of countless discrete elements working together to maintain coherence. Space feels continuous for the same reason a digital image looks smooth from a distance. The resolution is hidden by scale. The deeper discomfort comes from what this says about fundamentality. You trust space because it feels unavoidable. You exist somewhere. You move from one place to another. But if space is emergent, then existence is not grounded in location. It is grounded in structure. You are not embedded in space in the way you assume. You are embedded in an informational pattern that gives rise to the sensation of space. Reality, as an error-correcting code, suggests that the universe is not held together by material, substance, but by constraints. rules that prevent inconsistency, redundancies that protect structure, correlations that maintain coherence. What feels solid and continuous may be the surface expression of something discrete, abstract, and deeply non-intuitive. Space does not explain stability. Stability explains space, and once you accept that, the idea of space as the foundation of reality begins to dissolve. 13. The simulation argument without computers. You associate simulations with technology, but the argument does not require machines. It follows from probability. If realities capable of producing conscious observers can be generated in large numbers, then most observers are statistically likely to be inside generated environments. The unsettling part is not artificiality. It is that the argument remains valid regardless of how simulations are implemented. You tend to imagine simulations as deliberate constructions, servers running code, advanced civilizations creating digital worlds. This imagery makes the idea feel speculative, even anthropocentric. Remove the computers, and the argument still holds. In fact, it becomes harder to dismiss. The core of the simulation argument is not about hardware. It is about counting. If a process exists that can generate conscious observers, and if that process can be instantiated many times, then the majority of observers produced by that process will belong to the most numerous class. This is not a claim about intention or design. It is a consequence of arithmetic. Now consider your situation. You are a conscious observer experiencing a structured environment governed by regular laws. If there exists any mechanism that can generate environments like this more efficiently or in greater numbers than the one you assume to be fundamental, then statistically, you are more likely to be in one of those generated environments than in the original. The argument does not require silicon. It does not require programmers. It does not even require intelligence. It only requires replication. A simulation in this context is not a video game. It is any physical or mathematical process that instantiates the same conscious experiences under different underlying conditions. A simulated world could be implemented in another universe, in exotic physical substrates, or in abstract informational structures. The details do not matter. What matters is multiplicity. If base reality can give rise to one set of observers, and derived realities can give rise to many, then observers like you are overwhelmingly likely to be derived. You might object that such derived realities are unlikely or impossible, but this objection shifts the burden. You must argue not only that simulations are rare, but that they are fundamentally prohibited, not technologically difficult, not ethically avoided, physically impossible. This is a strong claim. Even modest assumptions lead to uncomfortable conclusions. If a civilization survives long enough to run a large number of ancestor-like environments, then the number of simulated observers quickly dwarfs the number of original ones. You do not need perfect fidelity. You do not need infinite detail. You only need enough structure to support experience. The unsettling feature is that nothing in your experience distinguishes base reality from a generated one. The laws feel consistent. The world responds predictably. Memories cohere. None of these are evidence of fundamentality. They are requirements for any environment capable of sustaining observers at all. The argument becomes more disturbing when you remove intentionality entirely. Even without civilizations, natural processes could generate observer-containing subsystems. Cosmological models with branching regions, repeated structures, or recursive physical laws could produce countless environments that mirror one another statistically. You do not need someone running a simulation. You only need a universe that produces many universes. At that point, the word simulation becomes misleading. What matters is that reality is not unique. You assume that the world you inhabit is the primary instance, that it is not a copy of anything else. The simulation argument challenges this assumption not by proposing deception, but by questioning typicality. Why assume you are in the rarest class of observers when more common classes exist? This does not mean your experiences are fake. Pain hurts. Meaning matters. Causality operates. A generated environment is still a real environment. The unsettling part is epistemic. You cannot tell what level of reality you occupy, because all levels capable of hosting experience must look internally coherent. The argument does not conclude that you are in a simulation. It concludes that if certain conditions hold, then it would be irrational to assume you are not. This is what makes it difficult to dismiss. It does not rely on science fiction. It relies on probability and self-location. You locate yourself as an observer in a large reference class of possible observers. Without additional information, you should expect to be typical within that class. If most observers are generated rather than fundamental, then so are you. The simulation argument without computers does not suggest a hidden operator or an artificial cage. It suggests something quieter, that the reality you experience may not be the base layer of existence. That fundamentality is not something you can feel from the inside. And once that possibility is admitted, the idea that this world is the ultimate one becomes an assumption, not a fact. 14. The Boltzmann brain problem. You trust memory as evidence of history. But statistical mechanics allows for conscious entities to arise spontaneously from random fluctuations, complete with false memories. Given infinite time, these observers outnumber evolved minds. This implies that your memories may be more likely to be hallucinations than records. The paradox does not question consciousness. It questions whether continuity can be trusted at all. Your confidence in the past rests almost entirely on memory. You remember waking up earlier today. You remember yesterday. You remember a childhood that feels distant but coherent. These memories form a chain that convinces you that you are the product of a long, continuous history. Without them, the idea that the world existed before this moment would collapse. Physics offers a quieter, more disturbing possibility. In statistical mechanics, systems explore all allowed configurations given enough time. Order is rare, but not forbidden. Complex structures can arise not only through gradual evolution, but through chance fluctuations. In a universe that lasts long enough, even extremely unlikely configurations will eventually occur. Among those configurations are brains, not metaphorical brains. Physical systems identical to yours in structure, state, and function. Systems that generate conscious experience. Systems that contain memories, expectations, and a sense of identity. From the inside, there is no difference between a brain that arose through billions of years of cosmic evolution and one that assembled momentarily due to random fluctuation. The latter is called a Boltzmann brain. A Boltzmann brain would experience a world. It would remember a past. It would believe it had a history. None of that history would be real. The memories would be part of the fluctuation itself. There would be no corresponding events that actually occurred. This is not a claim about psychology. It is a claim about probability. In many cosmological models, especially those involving infinite or extremely long-lived universes, random fluctuations are unavoidable. Over vast timescales, the spontaneous appearance of isolated conscious systems becomes statistically inevitable. More troublingly, these systems may vastly outnumber observers produced by orderly processes like evolution. If that is the case, then a randomly selected conscious observer is more likely to be a Boltzmann brain than an evolved one. You are a randomly selected conscious observer. This is where the paradox sharpens. You believe you are embedded in a stable universe with a long past because your memories tell you so. But Boltzmann brains also have memories that tell them the same thing. There is no internal test that distinguishes a genuine memory from a fabricated one. Conscious experience alone cannot certify its own history. The problem is not that Boltzmann brains are likely in a practical sense. In our current universe, they may be extraordinarily rare. The problem is that in certain otherwise plausible cosmological models, they dominate in principle. If your theory predicts that most observers are deluded about their past, then something has gone wrong. Either the theory is incorrect or your confidence in memory is unjustified. Physicists take this seriously. The Boltzmann brain problem is not treated as a curiosity. It is used as a criterion to reject cosmological models. A universe that predicts an overwhelming number of Boltzmann brains is considered unacceptable, precisely because it undermines the reliability of observation itself. But this move exposes the depth of the issue. The reason such models are rejected is not because Boltzmann brains are impossible. It is because accepting them would dissolve the foundation of empirical reasoning. If most observers are hallucinating their histories, then evidence loses its authority. You rely on the assumption that your memories track real events. Science relies on the same assumption. The Boltzmann brain problem reveals that this assumption is not guaranteed by physics alone. It must be protected by the structure of the universe. This shifts the question from psychology to cosmology. It is not enough for a universe to produce consciousness. It must produce it in a way that makes memory reliable. Continuity must be enforced statistically, not just locally. The paradox does not suggest that you are a Boltzmann brain. It suggests something more unsettling. That your certainty about not being one depends on global features of the universe you cannot directly observe. You feel anchored in a long past. Physics allows for minds that feel the same way without having one. The difference between the two is not experiential. It is structural. And that means the trust you place in memory is not a given. It is a fragile achievement of the universe itself. 15. Fine-tuning without design. The universe appears balanced. Physical constants sit within narrow ranges that allow complexity. Too much deviation in stars, chemistry, or structure collapse. Some see design. Others invoke multiverses. Both explanations are unsatisfying. Either reality is improbably tuned without reason, or explanation is deferred beyond observation. The coincidence remains. You encounter this balance indirectly. Atoms hold together. Stars burn steadily for billions of years. Chemistry supports molecules complex enough to store information and replicate. None of this is guaranteed. Change a few numbers slightly, and the structure you depend on disappears. The strength of fundamental forces, the masses of elementary particles, the rate of cosmic expansion. These parameters appear delicately set, not optimized for life in a general sense, but constrained just enough to allow long-lived structure. A universe that deviates even modestly from these values becomes sterile. Matter collapses too quickly, or it never clumps at all, or complexity dissolves before it can begin. This fragility is not intuitive. You expect robustness. You expect that many combinations of laws could produce something like a world. Instead, physics suggests a narrow corridor, a small region of possibility in an otherwise hostile landscape. One response is to see intention. If the parameters are tuned, perhaps they were chosen. This explanation feels immediate because it aligns with everyday reasoning. When you see a delicate arrangement that achieves a specific outcome, you infer design. But this inference raises more questions than it answers. Who or what selected the parameters? By what mechanism? According to what criteria? Introducing intention explains the coincidence by relocating it, not resolving it. The other response is to deny uniqueness. If many universes exist, each with different parameters, then it is not surprising that at least one supports complexity. You find yourself in such a universe because you could not exist anywhere else. This is selection, not design. This explanation avoids intention, but at a cost. The multiverse is not directly observable. Its existence is inferred to explain a coincidence within the part you can observe. Explanation is deferred beyond empirical reach. The tuning remains unexplained within your universe. It is outsourced. Both approaches share a problem. They explain why you observe a life-permitting universe, but not why the underlying space of possibilities has the structure it does. Why these parameters? Why this distribution? Why laws that allow tuning at all? The fine-tuning problem is not that life exists. It is that the conditions allowing complexity appear compressed into an improbably small region of theoretical space. This compression demands explanation, regardless of whether you invoke design or multiplicity. You might try to dissolve the problem by arguing that life adapts to whatever laws exist, but this misunderstands the constraint. The issue is not that life requires specific conditions. It is that complexity itself does. Stars, chemistry, and stable structures are prerequisites for any known form of organization. Without them, there is nothing to adapt. The discomfort deepens when you realize that fine-tuning does not only concern life, it concerns predictability, stability, and persistence. A universe slightly different from this one does not merely lack observers, it lacks structure. This raises a quiet but profound question. Are the laws of physics contingent or necessary? Could they have been otherwise? If they could, why do they sit where they do? If they could not, why does necessity take this form? You expect fundamental laws to explain phenomena, not to be phenomena themselves. Fine-tuning blurs this distinction. The laws begin to look like outcomes that require explanation, rather than explanations that terminate inquiry. This does not push you toward mysticism, it pushes you toward humility. The coincidence remains not because it is mysterious in a vague sense, but because it resists reduction. Every attempt to explain it either introduces entities you cannot observe or assumptions you cannot justify. Fine-tuning without design leaves you with an unresolved imbalance, a universe that appears calibrated without an identifiable calibrator, a structure that permits complexity without revealing why complexity is permitted at all. You live inside this balance. You depend on it at every moment, and yet its origin remains opaque, not hidden, but unanswered. The coincidence remains. 16. The anthropic trap. You reason that the universe must allow observers because you are here. But this reasoning cannot predict anything independently. It filters explanations after the fact. The anthropic principle explains survival, not origin. It removes the ability to ask why these laws exist instead of others. Understanding becomes selection bias disguised as insight. The logic feels harmless. You observe a universe compatible with your existence, so of course it must be compatible with observers. If it were not, you would not be here to notice it. This reasoning feels almost tautological, and that is precisely the problem. The anthropic principle does not explain why the universe has the properties it does. It explains why you observe those properties given that you exist. It conditions observation, not reality. It tells you what must be true for you to be here, not what caused it to be true. This distinction is easy to blur. When confronted with fine-tuning, the anthropic principle offers relief. The constants appear balanced because only balanced universes contain observers. There is no mystery, only selection. But this relief is shallow. It replaces explanation with exclusion. Universes that do not permit observers are ignored, not explained. You are left knowing why you do not observe hostile universes, but still ignorant of why the space of possibilities is structured the way it is, why the laws allow any observers at all, why the parameters cluster where they do. The anthropic principle remains silent. This silence becomes dangerous when it is mistaken for understanding. You might feel that invoking the anthropic principle closes the question, that asking why the universe permits observers is meaningless, because the answer is self-evident. But this is a trap. It shifts the burden of explanation from physics to perspective. It tells you not to ask certain questions, not because they are incoherent, but because they are uncomfortable. In doing so, it risks turning explanation into hindsight. Imagine applying the same reasoning elsewhere. You survive a rare event and conclude that the event must have been survivable because you survived it. This is true, but it explains nothing about the event's probability or cause. It only reflects the fact that you are observing from a non-random position within the outcome space. Anthropic reasoning identifies this non-random position. It does not explain why the outcome space has the structure it does. In cosmology, this matters because you are trying to explain laws, not observations. Laws are supposed to be primary. They determine what can happen. When you use the anthropic principle as an explanation, you reverse this relationship. Observations determine which laws you consider. This inversion quietly dissolves the ambition of fundamental physics. You are no longer asking why reality has these properties. You are only explaining why you find yourself in a region where they hold. The deeper question of origin is deferred indefinitely. This becomes especially problematic when anthropic reasoning is combined with multiverse hypotheses. If all possible laws exist somewhere, then no particular set of laws requires explanation. You observe these laws because you could not observe others. End of discussion. But this is not an explanation. It is a refusal to explain. You still have no account of why all possible laws exist, why the multiverse has the structure it does, why the distribution of parameters permits complexity at all. The anthropic principle filters, but it does not generate. The trap lies in its plausibility. Anthropic reasoning is valid as a constraint. It correctly notes that observations are conditioned by the observer's existence. But when elevated to a primary explanatory principle, it becomes circular. It explains observations by appealing to the necessity of those observations. You are left with a universe that is compatible with you, but unexplained. Understanding becomes selection bias with mathematical polish. Insight becomes survival dressed as necessity. The anthropic trap does not claim that the universe was designed for observers. It claims something subtler and more corrosive, that the fact you are here is enough, that no deeper explanation is required. If accepted too readily, this dissolves the motivation to seek fundamental causes at all. It encourages you to stop at the point where explanation becomes uncomfortable. You survive in this universe. That fact is undeniable. The anthropic trap is mistaking that fact for an answer. 17. Gödel's shadow over physics. You assume a complete description of reality exists. Gödel's incompleteness theorems say otherwise. Any sufficiently complex formal system contains true statements that cannot be proven within it. If physics is formalizable, then some truths about reality may be unprovable by physical theory itself. Understanding hits a logical ceiling. You expect physics to move steadily toward completion. Each discovery fills a gap. Each equation clarifies what was once mysterious. The hope is not merely better prediction, but closure. A final framework that explains everything that can be explained. Gödel's theorems quietly challenge this hope. They begin with a simple observation about formal systems. Any system rich enough to encode arithmetic will contain statements that are true, but cannot be proven using the rules of that system. This is not a limitation of ingenuity or time. It is structural. No amount of refinement removes it. The system cannot certify all of its own truths. This result was originally about mathematics, not physics. But physics relies on mathematics to describe reality. If the laws of nature can be fully formalized, if they can be written as a consistent set of mathematical rules, then Gödel's shadow falls across them as well. There may be facts about the universe that are true, but inaccessible to proof within the framework used to describe it. This is not the same as ignorance. It is not a gap waiting to be filled by better experiments or more powerful computation. It is a boundary, a limit imposed not by nature's complexity, but by logic itself. You might try to escape by arguing that physics is empirical, not purely formal. That experiments settle questions mathematics cannot. But experiments still require interpretation. They still rely on theoretical structures to connect measurement to meaning. If the underlying framework is formal, then its limitations remain. Even worse, attempts to strengthen the system by adding new axioms do not solve the problem. Each extension produces a new system with its own unprovable truths. The ceiling rises, but it never disappears. This forces a reconsideration of what explanation means. You tend to think of explanation as reduction, breaking phenomena down into simpler components until nothing remains unexplained. Gödel's theorems suggest that reduction cannot reach the bottom. There will always be statements that are meaningful, true, and unreachable from within the system. Applied to physics, this implies that reality may contain facts that no physical theory can derive, even in principle. Not because they are hidden, but because deriving them would require stepping outside the system that defines what derivation is. You may feel tempted to dismiss this as abstract, but the implications are concrete. If some truths about the universe are undecidable within physical theory, then prediction has limits that are not merely practical. There may be questions you can ask about reality that have definite answers, but no method within physics to obtain them. This is not uncertainty in measurement. It is uncertainty in principle. The unsettling part is not that knowledge is incomplete. It is that completeness may be unattainable. The dream of a final theory that answers all meaningful questions about reality may be logically incoherent. This does not render science pointless. It sharpens it. Science becomes a process that maps what can be known, while acknowledging that the map cannot cover everything. The unknown is not a temporary embarrassment. It is a permanent feature. Gödel's shadow suggests that explanation has an internal horizon. You can approach it, you can push it back, but you cannot cross it. This also reframes certainty. You may believe a statement about the universe that cannot be proven within your best theory. You may even be justified in believing it, based on indirect reasoning or empirical patterns. But proof, in the formal sense, may be unavailable. Reality becomes larger than its description. You are accustomed to thinking that if something is true, it must be provable given enough effort. Gödel shows that truth and provability can diverge. Applied to physics, this means that the universe may contain truths that are real, precise, and forever beyond formal capture. Understanding does not fail because the universe is chaotic or mysterious. It fails because logic itself imposes a limit. Gödel's shadow does not tell you which truths are unreachable. It tells you that some are, and that means the project of fully explaining reality is constrained from the start. The universe may be intelligible, it may be describable, but it may never be exhaustible by description. 18. Self-reference in the laws of nature. Observers emerge from the universe, then attempt to describe it. This creates a loop. The system contains entities that define the system. Self-reference generates paradoxes in logic. Physics increasingly relies on observer-dependent frameworks. The universe becomes partially defined by processes that arise within it, erasing any clean separation between subject and object. You are not outside the world you study. You are made of the same matter, governed by the same laws, embedded in the same space-time you attempt to describe. This seems obvious, even reassuring. But when taken seriously, it introduces a problem that physics cannot avoid. Any complete theory of the universe must include observers. But observers, by definition, are the entities who formulate the theory. The universe is required to contain a description of itself being described. This is not metaphorical. It is structural. In logic, self-reference is dangerous. Systems that refer to themselves generate contradictions, undecidable statements, or infinite regress. The classic examples are familiar. Statements that assert their own falsehood, rules that apply to themselves. These are not curiosities. They reveal limits in what formal systems can consistently express. Physics increasingly faces a similar loop. Quantum theory relies on measurement. Measurement requires an observer, or, at minimum, an observational context. The theory predicts outcomes, but only relative to how and what is measured. The observer is not merely a passive recorder. Observation enters the formalism as an active ingredient. Relativity complicates this further. Observers moving differently experience different divisions of space and time. There is no single, observer-independent structure of simultaneity. What counts as now depends on who you are and how you move. The universe does not present a single timeline. It presents many, each tied to an observer's frame. These frameworks work. They predict with extraordinary accuracy, but they do so by abandoning the idea that reality can be described entirely without reference to the entities doing the describing. You might try to remove the observer by reducing it to a physical system like any other, a measuring device, a collection of particles. But this does not dissolve the loop. The description still requires a boundary between what is being described and what does the describing. Shifting the boundary does not eliminate it. It only relocates it. If the observer is fully included in the system, then the system must describe its own description. The theory becomes reflexive. This is where the discomfort sharpens. A universe that contains observers capable of modeling the universe cannot be fully captured by a single, detached description. Any such description would have to include itself as part of what it describes. The distinction between map and territory collapses. You expect laws of nature to be objective, to exist independently of who observes them. But if the formulation and application of those laws depend on observational context, then objectivity becomes conditional. Not false, but incomplete. This does not mean reality is subjective. It means that subject and object cannot be cleanly separated at the deepest level. The observer is not an external add-on. It is a feature of the universe that feeds back into how the universe is described. This creates a subtle instability. The universe gives rise to observers. Observers give rise to theories. Theories attempt to describe the universe that produced the observers. The loop closes. Within this loop, certain questions become problematic. Can a system fully predict its own future behavior? Can a theory that includes observers predict the choices of the observers who formulate and apply it? Can a description be complete if it must include the act of description itself? These are not philosophical distractions. They appear in concrete forms, from limits on prediction to observer-dependent realities. The deeper physics goes, the more it encounters frameworks where the observer cannot be eliminated without breaking the theory. The clean separation you rely on in everyday thinking, the idea that there is a world out there and a mind in here, becomes an approximation. Useful, but not fundamental. Self-reference suggests that reality may not admit a view from nowhere. There may be no perspective from which the universe can be described without remainder. Every description carries the imprint of the context in which it was produced. You are part of the system you seek to understand. That fact does not make understanding impossible. It makes it incomplete by nature. The laws of nature may still exist. They may still constrain behavior. But their formulation, interpretation, and application are inseparable from the observers who arise within the very structure those laws govern. The universe does not merely allow observers. It reflects itself through them, and in doing so, it entangles explanation with existence in a way that cannot be fully unraveled. 19. Consciousness as an unavoidable variable. You treat consciousness as secondary, a byproduct, but many physical interpretations cannot avoid referencing observers. Measurement, experience, and information acquisition play structural roles. Whether consciousness is fundamental or emergent, it refuses to be irrelevant. Reality seems incomplete without accounting for experience itself. You are encouraged to think of consciousness as something that happens after the real work is done. Matter arranges itself, neurons fire, chemistry unfolds, and somewhere along the way, experience appears. In this picture, consciousness adds nothing. It watches, it reports, it has no causal weight. Modern physics complicates this dismissal. At multiple points, the formal description of reality quietly relies on concepts that resemble experience. Measurement is not just interaction, it is the acquisition of information. Outcomes are not just states, they are registered results. The theory does not merely describe what exists, it describes what can be known. This creates an uncomfortable overlap. Knowledge is not a physical object, experience is not a particle, and yet the framework seems incomplete without them. You might insist that consciousness can be reduced, that it is fully explained by brain processes, which are in turn explained by physics. But even if this reduction succeeds, it does not remove the role consciousness plays in interpretation. The equations tell you what outcomes are possible. They do not tell you what it is like for an outcome to occur. This distinction is easy to ignore until it becomes unavoidable. In quantum theory, probabilities are assigned to potential measurement results. But probabilities are meaningless without something that experiences an outcome. A probability does not collapse itself. It is resolved only when an outcome is registered. The theory does not say what counts as registration in purely physical terms. You can attempt to replace consciousness with devices, detectors, records, environmental interactions, but this substitution only pushes the problem back. A record is meaningful only relative to a system that can interpret it. Information requires a receiver, even if that receiver is later included in a larger description. The problem is not that consciousness violates physics. The problem is that physics quietly presupposes something like it. This leads to a deeper question. Is consciousness fundamental, like space and time, or is it emergent, like temperature and pressure? Either answer carries discomfort. If consciousness is fundamental, then reality includes experience as a basic component. The universe is not purely objective. It contains subjectivity at its core. This challenges the idea that physics describes a world entirely independent of observers. If consciousness is emergent, then you must explain how subjective experience arises from objective processes. Not behavior, not function, experience itself. Why there is something it is like to be a system at all. Physics, as currently formulated, has nothing to say about this transition. Either way, consciousness cannot be ignored. It is either part of the foundation or a gap in the structure. What makes this unsettling is not mystery, but persistence. Every attempt to eliminate consciousness from the explanatory picture ends up reintroducing it indirectly, through observation, through information, through reference frames, through interpretation. You may try to maintain that consciousness is irrelevant to the universe as a whole, that the universe existed long before minds and will exist long after. This may be true, but irrelevance is not the same as dispensability. The question is not whether consciousness is common, it is whether a complete account of reality can omit it entirely. So far, it has not. The universe you describe is always the universe as described. There is no access to a world without perspective. Even the most objective theory is formulated, tested, and understood by conscious systems embedded within the reality they study. This creates a subtle inversion. You think of consciousness as something inside the universe. Physics, increasingly, treats the universe as something that cannot be fully specified without reference to observation. The boundary blurs. You are not simply a bystander witnessing reality. You are a locus where reality becomes definite, meaningful, and structured, not because you are special, but because experience is the point at which description terminates. The discomfort is not that consciousness is mysterious. It is that it may be unavoidable. That no matter how far physics progresses, there remains a variable that cannot be eliminated without erasing the conditions under which explanation itself operates. Reality may function without you, but understanding reality may not. And that leaves consciousness in a strange position, not as an add-on, not as an illusion, but as something that refuses to be placed neatly on either side of the line between observer and world. The universe may be complete without experience, but any account of it is not. 20. The hard problem refuses reduction. You can describe neural activity, signals, correlations, patterns. None of these explain why experience exists at all, why there is something it is like to be you. Physics explains structure and behavior. It does not explain presence. The gap remains unbridged despite centuries of progress. You are told that consciousness will eventually be explained the way life was explained, once mysterious, now understood in terms of chemistry and evolution. The implication is that experience is merely the next puzzle waiting for sufficient detail. Map the brain completely, and the mystery will dissolve. But this confidence conceals a category mistake. Descriptions of neural activity tell you what the brain does. They tell you how information flows, how signals integrate, how behavior emerges. They do not tell you why any of this is accompanied by experience, why electrical activity should feel like anything at all, why there is a first-person perspective rather than only processes. This is the hard problem. It is not a problem of complexity. Adding more detail does not bring you closer. You can trace every neural pathway, simulate every synapse, reproduce every functional relation, and still be left with the same unanswered question. Why is there presence rather than silence? You might try to dissolve the problem by redefining consciousness as behavior or reportability. If a system acts as though it is conscious, then it is conscious. But this move avoids the issue rather than addressing it. Acting conscious is not the same as being conscious. A description of outputs does not explain experience. You can imagine a system that behaves exactly like you, speaks as you do, reacts as you do, and yet has no inner life at all. Whether such a system is possible is debated. What matters is that nothing in physics rules it out. The equations do not specify experience. They specify relations. This reveals a limit of reduction. Reduction works when higher-level phenomena can be fully accounted for by lower-level descriptions. Temperature reduces to molecular motion. Pressure reduces to collisions. But experience does not reduce to function in the same way. No rearrangement of objective facts seems to entail subjective presence. This does not mean experience violates physics. It means physics is silent about it. The silence is striking because experience is the one thing you cannot doubt. You can doubt theories. You can doubt interpretations. You cannot doubt that something is happening from the inside. And yet, the most successful description of the universe has nothing to say about this fact. You might hope that future physics will close the gap. But notice what would be required. A physical theory would need to explain not only how systems behave, but why certain states are accompanied by experience and others are not. It would need to connect objective structure to subjective presence without redefining one into the other. So far, no framework does this. Some propose that consciousness is fundamental, that experience is a basic feature of reality, like mass or charge. This avoids reduction by expanding ontology, but it raises new questions. How does fundamental experience combine? Why does it appear localized? Why does it correlate so precisely with certain physical processes? Others maintain that consciousness is emergent, that it arises when complexity crosses a threshold. But emergence explains patterns, not presence. Complexity can produce behavior. It does not explain why behavior is felt. The hard problem persists because it is not about how the brain works. It is about why working feels like anything at all. This creates a quiet tension with physicalism. If physics is complete in describing the world, and if consciousness is part of the world, then physics should account for it. If it does not, then either physics is incomplete, or consciousness is not fully part of the physical description. Neither option is comfortable. You may try to ignore this gap, treating it as a philosophical curiosity with no bearing on reality. But the gap sits at the center of experience. Every measurement, every observation, every piece of knowledge occurs within it. The subjectivity you cannot explain is the condition under which explanation happens. The hard problem refuses reduction, not because science has failed, but because its methods target the wrong kind of question. Physics explains relations between things. Experience is not a relation between things. It is the presence in which relations appear. You are not troubled by this gap in everyday life. You live within experience, not outside it. But once you ask what reality is ultimately made of, the gap becomes impossible to ignore. The universe you describe is silent about the fact that it is being experienced. And yet that fact is the one from which all description begins. The hard problem remains, not as an anomaly, but as a reminder. That understanding structure is not the same as understanding presence, and that something essential about reality may lie precisely where explanation runs out. 21. Identity over time is not preserved. You assume continuity of self, that you persist from moment to moment. But physics allows no clear boundary where identity is conserved. Cells replace themselves, memories reconstruct. Conscious moments do not overlap. The sense of a persistent self may be a narrative imposed on discontinuous processes. You experience yourself as a single entity moving through time. You woke up this morning as the same person who went to sleep. You recognize your thoughts as yours. You feel ownership over memories that stretch back years. This continuity feels so obvious that questioning it seems artificial. Physics offers no mechanism that guarantees it. At the biological level, your body is in constant flux. Cells die and are replaced. Molecules are exchanged with the environment. Even the structures of your brain are not fixed. Neural connections strengthen, weaken, and reconfigure. There is no static material core that remains unchanged across time. You might think identity is preserved by memory. You are the same person because you remember being that person. But memory is not a stable record. It is reconstructed each time it is accessed. Details shift. Emotions reframe events. Entire memories can be altered or fabricated without detection. The past you remember is not retrieved. It is rebuilt. Physics does not recognize memory as a conserved quantity. There is no law that preserves personal history the way energy or information is preserved. Memory is a pattern, not a substance. Patterns can change while maintaining the illusion of continuity. At the level of conscious experience, the problem sharpens. You do not experience multiple moments at once. Each conscious moment is self-contained. When a new moment occurs, the previous one is gone. There is no overlap. There is no continuous stream you can directly observe. What you call continuity is inferred, not experienced. From the inside, this inference feels seamless. Each moment contains memories of previous moments, creating the impression of persistence. But nothing in the physics of the moment requires that the experiencer is numerically identical to the one before. There is only similarity and causal connection. This raises a quiet question. What does it mean to be the same person over time? In physics, identity is not fundamental. Objects are defined by their properties at a given time. Over time, those properties can change continuously or discontinuously. There is no intrinsic marker that says this object now is the same object as before. Identity is imposed by how you track systems, not by the systems themselves. You assume that identity persists because change appears gradual, but gradual change does not imply numerical sameness. A sequence of similar states is not the same thing as a single enduring entity. It is a chain, not a point. This becomes clearer in extreme cases. Amnesia can sever memory while leaving personality partially intact. Brain injury can alter personality while leaving memory intact. Sleep, anesthesia, and unconsciousness interrupt experience entirely. And yet you speak as though the same self passes through these gaps unchanged. Physics does not justify this language. It tolerates it as a useful approximation. From a strictly physical perspective, what exists at each moment is a configuration. That configuration includes a brain state that encodes memories, dispositions, and expectations. The next moment contains a related configuration. The link between them is causal, not identical. You might object that this undermines responsibility or meaning, but those concepts already rely on continuity being approximate, not absolute. You hold someone accountable because their present state is causally connected to past actions, not because some metaphysical self persisted unchanged. The discomfort arises when you realize how much of your sense of self relies on narrative. You tell a story about being the same person over time because the story is functional. It allows planning, learning, and social coordination. But functionality is not fundamentality. The self you experience may be less like an object and more like a process, or even less than that. A pattern that recreates itself moment by moment, sufficiently similar to sustain the illusion of persistence. Physics does not deny that you exist. It denies that existence comes with an intrinsic label of sameness over time. Identity is not something the universe preserves. It is something you infer. You live as though there is a single you enduring across moments. The deeper description suggests something colder, a succession of closely related states, each convinced it is the continuation of the last. The narrative holds because the transitions are smooth, but smoothness is not identity. And once you see that, the question changes. You stop asking whether you will be the same person tomorrow. You start asking what that question ever meant. 22. Determinism without predictability. You fear determinism because it removes freedom, but even deterministic systems can be fundamentally unpredictable. Chaos amplifies uncertainty beyond measurement. Outcomes become unknowable in practice, even if fixed in principle. Control dissolves not because rules fail, but because they are too precise to track. You tend to equate determinism with certainty. If the laws are fixed and the state of the world at one moment fully determines the next, then the future should be knowable. Given enough information and enough computation, everything should be predictable. This is the image that makes determinism feel threatening. It suggests a locked future, already written. Physics does not support this comfort. Deterministic laws do not guarantee predictability. In many systems, tiny differences in initial conditions grow exponentially over time. This is not noise or randomness. It is a direct consequence of the equations themselves. The system is fully deterministic, yet its future becomes inaccessible. This is chaos. In a chaotic system, knowing the laws is not enough. You must know the initial conditions with infinite precision. Any finite error, no matter how small, eventually overwhelms prediction. Two states that are indistinguishable by any practical measurement diverge into completely different outcomes. The problem is not that measurement is sloppy. It is that perfect measurement is physically impossible. There are limits imposed by quantum uncertainty, thermal noise, and finite resolution. You can never specify the exact state of a real system, and in chaotic dynamics, this limitation is fatal to prediction. The future becomes unknowable, even though it is fixed. This undermines a common fear about determinism. The fear assumes that if outcomes are determined, they are accessible, that the universe is a machine whose behavior can, in principle, be calculated. chaos reveals a different picture. The machine exists, but its workings outrun any attempt to track them. Weather is the familiar example. The equations governing fluid dynamics are deterministic, yet long-term weather prediction fails, not because the laws are probabilistic, but because the system amplifies uncertainty faster than information can be refined. Now, generalize this. Complex systems pervade reality. Ecosystems, brains, societies, even simple physical systems can exhibit chaotic behavior. Determinism does not tame them. It renders them opaque. This creates a subtle inversion. Randomness is often associated with unpredictability. Chaos shows that unpredictability can arise without randomness at all. The universe can be fully lawful and still surprise you at every turn. From the inside, this feels indistinguishable from indeterminism. You make decisions without knowing their consequences. You act without certainty. You learn outcomes only after they occur. The fixed nature of the future does not translate into foresight or control. This matters for freedom. If freedom requires the ability to predict and manipulate outcomes, then even an indeterministic universe would not guarantee it. And if freedom requires that the future not be fixed, chaos shows that fixation does not imply transparency. A determined future can be as inaccessible as an undetermined one. The discomfort comes from realizing that loss of control does not require randomness. It arises naturally from precision itself. The rules are not vague, they are exact, and that exactness makes them unforgiving. You might imagine an ideal observer with infinite precision and infinite computational power. Such an observer could, in principle, predict everything. But this observer cannot exist within the universe it predicts. It would require resources that exceed physical limits. Predictability becomes a property of a hypothetical outside perspective, not of reality as experienced from within. From where you stand, the future is open in practice, even if closed in principle. This erodes a simple opposition: determinism versus freedom, predictability versus choice. The universe does not arrange itself along these lines. It allows determinism without foresight, law without control, order without access. You are constrained by rules you cannot track, shaped by dynamics you cannot foresee. Your actions participate in chains of causation that extend beyond your capacity to calculate. This does not make your choices irrelevant. It makes them embedded. They matter because they alter the state of systems whose future trajectories depend sensitively on present conditions. Small actions can have large consequences, not because the world is random, but because it is precise. Determinism without predictability leaves you in a strange position. The future may already be fixed, but it is not available to you. You must act without knowing. You must choose without certainty. The threat to freedom was never determinism itself. It was the illusion that determinism implies mastery. Chaos removes that illusion. The universe can be lawful and still refuse to be controlled. 23. Free will as a constraint, not a power. You think free will allows anything. Some interpretations reverse this. Choices may be constrained to maintain consistency within the universe's structure. Actions that would produce contradiction simply never occur. Freedom exists, but only within allowable pathways. Choice becomes selection among necessities. You are accustomed to thinking of free will as openness, a space of possibilities stretching outward, where at each moment you could have acted otherwise. This picture feels inseparable from responsibility and agency. If you were not free to choose differently, then your choices would seem hollow. Physics and logic quietly challenge this picture. In several theoretical frameworks, the universe does not permit all logically imaginable actions. It permits only those that fit coherently within its global structure. Outcomes that would create contradiction are not corrected after the fact. They are never realized at all. This is not a moral restriction. It is not enforcement. It is consistency. In systems governed by strict laws, not every apparent option is physically available. You may feel free to choose anything, but the set of choices that can actually occur is narrower than the set you can imagine. The universe does not consult your intentions. It filters outcomes according to what can exist without breaking its own structure. From this perspective, free will is not the power to generate arbitrary outcomes. It is the experience of navigating a constrained space of viable ones. This becomes clearer when you consider extreme cases. You cannot choose to violate conservation laws. You cannot decide to make 2 + 2 = 5. You cannot will a contradiction into existence. These limitations feel trivial because they are obvious, but the same logic may apply more subtly to every decision you make. You deliberate, you consider alternatives, but the alternative that actually occurs is the one compatible with the total state of the universe, including its past, its laws, and its future coherence. Other imagined options dissolve, not because you rejected them, but because they were never fully available. This does not mean your deliberation is fake. The process of weighing options is itself part of the universe's structure. Your reasoning influences outcomes, but it does so within boundaries you do not control. Some interpretations of physics go further. They suggest that if a choice would lead to inconsistency at a global level, then the conditions required to make that choice simply never arise. The thought may occur, the intention may form, but something intervenes. Circumstances shift. The moment passes. The contradiction is avoided without announcement. From the inside, this feels like ordinary life. Plans change, opportunities vanish, decisions resolve in ways that feel contingent. From the outside, the structure remains coherent. This reframes freedom in an unsettling way. You are free not because anything can happen, but because multiple consistent pathways exist. Your will does not create possibilities from nothing. It selects among those that are already compatible with reality. Choice becomes a form of alignment, not creation. This challenges a common fear. You fear that if the universe is constrained, then freedom disappears. But consider the alternative. A universe that allowed any action whatsoever would collapse immediately into contradiction. Meaningful choice requires structure. Constraints are not the enemy of freedom. They are its precondition. Without constraints, there are no alternatives to weigh. There is no distinction between possible and impossible. Choice dissolves into noise. Seen this way, free will does not float above the universe as an exception to its rules. It operates within them as a process, a mechanism by which certain outcomes are selected over others, not arbitrarily, but coherently. The discomfort arises when you realize how little of this structure is visible to you. You feel free because you cannot see the full set of constraints shaping your decisions. You experience options because many pathways remain open. But the openness is partial, not absolute. You are not choosing from infinity. You are choosing from necessity. This does not make your choices meaningless. It makes them situated. Your decisions matter because they alter which consistent pathway is realized. They matter locally, even if the global structure is fixed. Free will, in this view, is not the power to break the universe. It is the power to move within it. And that is a quieter, heavier conception of freedom than the one you are used to 24. Reality may be incomplete by necessity. You expect answers to exist, but it is possible that reality cannot be fully described without contradiction, that incompleteness is not a failure of knowledge, but a feature of existence. The universe may operate in a state that no single framework can capture without residue. You are trained to believe that every well-posed question has an answer. If not now, then eventually. If not with current tools, then with better ones. This expectation underlies science itself. Progress means reducing mystery, closing gaps, eliminating paradox. But as you descend deeper into the structure of reality, a different possibility emerges. Not that answers are hidden, but that some answers cannot exist in the form you expect. In several domains, incompleteness does not appear as an accident. It appears as a requirement. You have already seen this pattern. Formal systems cannot prove all truths about themselves. Quantum theory cannot fully explain measurement without stepping outside its own rules. Time cannot be both fundamental and emergent without contradiction. Consciousness cannot be reduced without leaving something essential out. Each case points to the same unsettling idea. Reality may not admit a total description that is both complete and internally consistent. This is not ignorance, it is structure. You tend to think of contradictions as signs of error. Something has gone wrong. An assumption must be false. A theory must be incomplete. But there is another possibility. That contradiction is not a bug in the description, but a shadow cast by the thing being described. In such a universe, no single framework can capture everything without remainder. Each framework reveals certain aspects while obscuring others. When you attempt to unify them all, the seams show. Paradox appears not because the world is confused, but because it exceeds the capacity of any single descriptive system. This forces a shift in how you think about explanation. You expect explanations to terminate, to reach a foundation where questions stop. But what if there is no such stopping point? What if every attempt to ground reality introduces a new context that itself cannot be fully grounded? In that case, incompleteness is not temporary. It is permanent. This does not mean anything goes. The universe remains structured. Laws remain effective. Predictions remain accurate. But the idea that there exists a final contradiction-free account of everything may be misguided. Reality may be layered in such a way that different descriptions are required for different questions, and no meta-description can unify them without distortion. You already live with this without noticing. You use classical physics for everyday objects, quantum theory for particles, relativity for space-time, and psychology for minds. These frameworks overlap imperfectly. Their boundaries are negotiated, not erased. You might expect future theory to unify them seamlessly, but it is possible that unification does not mean elimination of tension. It may mean managing it. The discomfort arises because this challenges a deep assumption, that reality is ultimately simple, that beneath complexity lies a single, clean structure. Incompleteness suggests the opposite, that simplicity may be a local phenomenon, not a global one. The universe may be consistent enough to exist, but not consistent enough to be fully captured. This also reframes paradox. Paradoxes are not necessarily signs that something must be resolved. They may indicate regions where descriptive frameworks overlap imperfectly. Trying to eliminate them entirely may be like trying to flatten a curved surface without distortion. You expect knowledge to converge. to approach a final truth asymptotically. In an incomplete reality, knowledge may instead branch. Different domains develop their own internal coherence, with no guarantee of total integration. This does not make inquiry pointless. It makes it bounded. You can still learn. You can still predict. You can still understand aspects of the world with remarkable precision. What you cannot do is step outside all contexts at once and see reality whole. There may be no view from nowhere, no final language in which everything can be said without loss. Reality may be incomplete by necessity, not because it is flawed, but because it is too rich to be contained by a single account. Contradiction may not signal failure. It may signal depth. You expect answers to exist. Reality may respond with something quieter. That some questions dissolve not because they are meaningless, but because they demand more coherence than existence itself provides. And that may be the final constraint, not on knowledge, but on what it means for something to be real at all. 25. The final paradox is that it works. Despite everything, reality functions. Technology works. Predictions succeed. Experiments repeat. The paradoxes do not stop the universe from behaving consistently where it matters. This is the most disturbing fact of all. That contradiction does not halt existence, it sustains it. You would expect unresolved contradictions to break things, to produce instability, to render prediction impossible. In every other domain, inconsistency is a flaw. A system that contradicts itself cannot function reliably, and yet the universe does. Quantum theory contradicts classical intuition, but it builds the devices you rely on. Relativity distends space and time beyond recognition, but your GPS works because of it. Information seems both conserved and inaccessible. Time seems both fundamental and illusory. Observation both reveals and creates outcomes. None of this prevents reality from operating with extraordinary precision. The world behaves as though it is coherent, even when its descriptions are not. This is not a minor detail. It is the central tension running through everything you have seen. The paradoxes are not peripheral. They sit at the foundation. And yet they do not cause collapse. They coexist with reliability. You might expect that deeper understanding would resolve these contradictions, that with enough progress, they would disappear. But instead, they persist. They sharpen. They become more clearly defined as theories improve. This suggests something unsettling. That consistency at the level of behavior does not require consistency at the level of explanation. Reality does not wait for you to make sense of it. It does not pause until contradictions are resolved. It functions anyway. You depend on this every moment. When you touch an object, it resists. When you move, space responds predictably. When you act, effects follow. None of this requires you to know what time ultimately is, or whether the universe is local, or how measurement produces outcomes. The universe does not ask for conceptual permission. This reveals a quiet asymmetry. You assume that explanation underwrites existence, that the world behaves because it makes sense. The evidence suggests the opposite. Sense is something you impose on behavior that already works. The paradoxes remain because they do not interfere with function. They are tolerated because they do not disrupt outcomes. Reality is not obligated to be intuitively coherent. It is only obligated to be internally stable enough to persist. This forces a reevaluation of what explanation is for. You are accustomed to thinking that understanding explains why things work. But perhaps understanding is only an after-the-fact alignment, a way to organize behavior that already occurs. The universe does not need to resolve paradox to function. It only needs to avoid self-destruction. And it does. This raises a disturbing possibility. That contradiction is not an error state, but a generative one. That certain kinds of tension are not flaws, but requirements. The universe may rely on incompatibilities between descriptions to maintain stability across scales. Consider how different frameworks apply in different domains. Classical mechanics works where quantum effects cancel out. Quantum theory works where relativistic effects are negligible. Relativity works where gravity dominates. Each framework breaks down where another becomes necessary. The seams do not align, yet together they cover reality well enough to function. The universe is stitched together, not unified. From this perspective, the demand for a single seamless description may be misplaced. Reality may not be built to satisfy it. The expectation of total coherence may be a projection of human preference, not a property of existence. The most unsettling part is that this does not feel unstable. It feels normal. You live inside a system that should not work, given its unresolved foundations. And yet it does, with such reliability, that you build entire civilizations on top of it. You navigate paradox without noticing, because paradox does not announce itself at the level of experience. The universe behaves as though contradiction is acceptable, as long as it is compartmentalized. This is the final paradox. Not that reality is strange, but that it is usable, that despite incomplete explanations, conflicting frameworks, and unresolved foundations, the world remains dependable. Existence does not require your understanding. It does not require closure. It does not require resolution. It requires only that enough structure holds long enough for something to happen. And that is perhaps the most unsettling conclusion of all. That reality is not fragile because of its contradictions. It is resilient because of them. The universe works not because it is fully coherent, but because coherence is not the condition for existence. It is a convenience for observers. Reality does not wait to be explained. It simply continues.